All right, should be good. Yep.
Hello, honor students. Mr. Keister here. This is new for me, and so we're going to be doing our lessons online in this style here. I want to make sure, as I told you in class last Friday, the 13th, that I want things to try and remain as normal as they can for you guys in regards to getting you the material that I know you have to know, so that you're prepared for either AP Chem at some point in your high school chemistry education, or if this will be your last chemistry class, then you are absolutely most ready for your first round of chemistry classes in college. I don't want to compromise your chemistry education if I can't help it. I do not want to do that. So the plan is, however long we're out of school, where we can't actually come to school, I'm going to present you the lessons this way, just as if you guys were sitting here in a classroom. And then as far as the homeworks and so forth, I sent you guys an email yesterday. Actually, today is Tuesday, the 17th. I sent you an email yesterday kind of outlining what I was going to do. And before I leave here today, I'm going to make sure that the answer keys to all the lessons that are covered are posted and linked to my Canvas homepage, and also that these videos will be there as well so that you can see them. I haven't worked out the details yet on collecting your graded work. I haven't worked out the details yet on labs and tests. So that I'm not really worried about right now. Like I said, my main concern is to make sure that we continue, that you guys continue being able to learn the material. That's first and foremost for me. And so that's the way we're going to approach it. So as you can see behind me here, this would have been the do nows for yesterday. And by the way, I've updated the do nows and already updated them and uploaded them to my Canvas homepage. So those, as of right now, are current. And so you can see what we would have done in class each day had we been here. This would have been yesterday's. This was our lab that I fully intend to do once we return to school. This is a good one. This is a Kool-Aid and s'mores lab. I got it all ready for you. So our first day back, you know what? We're going to celebrate by having Kool-Aid and s'mores. You had the molality assignment that would have been due yesterday, the 16th. I did not end up collecting that because that information, those types of problems are on the review. And so that answer key, though, is available to you, or will be available to you on Canvas from my homepage. As far as the review, that was also due yesterday, and I was collecting that. So again, we'll make sure you check your work and then set that aside, and we'll figure that out later. So I'm going to go ahead and scroll up to today, which is actually, this is today, the 17th. And so this would involve pages 167, 68, 69. Oh, I'm sorry, it did not. I'm sorry. Whoops, let me unfreeze the screen. That would help. There we go. All right, so actually then today, the 17th, would involve pages 170, 171, and 172. We would have turned in the lab today, which I was going to collect. Again, we'll not worry about that right now. We'll start the packet 10-2 packet today on solution applications. We're going to learn about solution stoichiometry. So we'll get to that here in a minute. Okay, now I want to explain the on mastering. So I haven't yet, but I will go ahead and assign this mastering today. But again, remember, you are not obligated to do any work this week. Because, it was, as explained in my email, Dr. Handback said that this would actually be an extension of our spring break. However, with all the work that we're going to be covering this week and the week after our regular spring break, if you have time to do it, if you're bored or otherwise have time to do it, I would encourage you to do that so that once we do return to school via e-learning on April 1st, that you're not bombarded with work then. So that's up to you. If you want to take the extra week off, it's perfectly fine. It's okay. But just to understand that when we do get back to work, that if you choose not to do that, then you'll have some more work to do at that time when we do. So what I'm going to do with this is I am going to go ahead and assign it today as I was going to. And I realize it says it's due Friday, March 20th, but that is not true. I'm going to go ahead when I assign it, make it due Friday, April 3rd. So you will have through April 3rd to complete that mastering. So we don't have to worry about that right now. But there again, if you have time and want to do it, by all means, go ahead. It covered all of the solution concentration methods that we talked about last week: mass percent, molarity, the dilution equation, molality, and solution stoichiometry, which we are doing today. So I think that pretty much covers it. And I believe mole fraction is on there too. I think, not 100% sure about that. So, having said that, let's go to, oh, there I am. Let's go to the notes, which are right there. So these are the new notes for Unit 10, Part 2. So we'll get started on that. So mass and or volume relationships between reactants and products that are in solution are very similar to those in the solid or gas phases. In other words, they're all related through the mole, and stoichiometry is certainly can be used. The only difference is that now to calculate the number of moles for a substance that's in solution, molarity must be used rather than molar mass, or 22.4 liters. You know, when we're converting to moles in stoichiometry, if we started with a mass, we use molar mass to get to moles. If we started with a volume of a gas, we use 22.4 liters to get to moles. Now, if we're using a solution, then we have to use that solution's molarity, which remember is moles per liter, to get to moles. And so we have another version of stoichiometry that can be used to calculate quantitative relationships involving solutions. So here is that diagram, if you have it with you. And I want to just make a couple, give you a couple things about that. So again, in step one, we're going to start with some known quantity. If it's a mass, just like before, because remember, solution reactions, we're pretty much talking about single replacement and double replacement for the most part. Not always, but for the most part. And so we could involve a mass of something, and if so, then we would get to moles in step two with molar mass, just like we always have. But now if we're going to start with the volume of a solution, and that would have to be in liters because that's what molarity is, moles per liters, then in step two, we would use our molarity of our solution, of our known solution, to get to moles. All right. Step three is always the same, mole ratio between unknown and known. And then step four, if we were looking for a mass of a product, then we would use molar mass. If we were looking for the volume of a gas, we would use 22.4 liters. But if we are looking for the volume of another solution, then we would use that solution's molarity in step four. However, if you look, it would be inverted. The moles of the unknown solution would be on the bottom, and the 1 liter would be up top. Right, because remember that molarity is moles per 1 liter. All right, so that's the main difference here. Otherwise, stoichiometry works the same as it always has. All right, works the same as it always has. So, got two examples here to show you. So let's take a look at those. All right, so the first one asks, what volume of 1 molar H2SO4? So we're looking for a volume there. It's required to react completely with 38.2 mLs of 0.525 molar NaOH. So we're looking for a volume. This is the molarity of that solution. Here is the volume of our known solution. We have a molarity and a volume. So this is going to have to be in liters, since molarity is in moles per liter, as we said a little bit ago. So if we just divide by 1,000 and move the decimal 3 to the left, that would be 0.0832, or 382, sorry, 0.3, wow, 0.0382 liters. There we go. It's a little early in the morning, and I was up all night, by the way. I worked my other job last night. The bread business is brisk right now, so I got called into work. And then here is the molarity of our known solution. So as you can see, hopefully you recognize that this is indeed a double replacement reaction, and specifically an acid-base neutralization reaction. I would hope that you would also remember that double replacements are never redox, but yet they do have a net ionic equation. We'll talk about that a little later, just to review that. We need to balance the equation first. Obviously, that's paramount to stoichiometry. Need a couple of 2's there. Okay, so let's identify what we have. So we have 0.0382 liters of sodium hydroxide, and we know its molarity is 0.525 molar. We know the molarity of our H2SO4 is 1.00 molar, but we do not know its volume. So that is what we're trying to find. So we'll set up our stoichiometry just like normal. We're going to start with the volume. Since we're starting with our known as a solution, we're going to start with its volume, 0.0382 liters of NaOH. Put that over 1. We're going to use its concentration, its molarity, to get to moles. So that would be 0.525 moles of NaOH over 1 liter. So again, there's its concentration. The liters cancel. Mole ratio step, unknown to known. So looks like we have 1 mole of H2SO4 over 2 moles of NaOH. And those cancel. And then in our last step, since we're looking for the volume of the solution, we're going to use H2SO4's molarity for that. We're going to have to invert it because we want the moles on the bottom and the liters on the top. So it's 1 molar, so it'd be 1.00 moles of H2SO4 on bottom. So those cancel. 1 liter of H2SO4 on top. So again, we're using its molarity, but we have to invert it so that we can cancel the moles and end up with a volume unit. So when you do the math on that and look back at our original info, which is 3 sig figs is the least, that gives us an answer of 0.0100 liters of H2SO4. Leaving it in liters is fine. If for some reason it asks for it in mLs, we can just do a quick conversion, and it would be 10.0 mLs. The beauty of solution stoichiometry is the elimination of excess reactants, which means we are eliminating waste. All right. What this stoichiometry tells us is that if we take 10.0 mLs of H2SO4 and react it with 38.2 mLs of 0.525 molar NaOH, that because of that, that is the exact amounts of each of those reactants that will then yield our products. Both of them, in effect, are limiting reactants. Neither one is excess. There is no waste whatsoever. That is critical out there in the real world where wasting reactants means you're wasting money. And so solution stoichiometry, as any other stoichiometry, can help you eliminate that. Okay. So that would be the answer for that one. Let's go back and talk about a net ionic equation real quick, because we said with a double replacement reaction, acid-base neutralization reaction, there's going to be one. So I'm not going to write all that down, but remember, anything that's AQ would be split. So here we would have 2H plus 1s and an SO4 minus 2. Here we would have 2Na plus 1s and 2OH minus 1s. Here we would have 2Na plus 1s and an SO4 minus 2. And if you remember, in a double replacement reaction, there are going to be two spectator ions. In this case, they would be sodium and sulfate. And so once those are removed, the net ionic equation would be 2 hydrogen ions plus 2 hydroxide ions would yield 2 H2O liquids. Little review there on net ionic, which absolutely you need to know. All right, so let's look at the next one. Example 2, and if we take a quick look at this, I hope you see that this is a single replacement reaction. Calcium is far more reactive than hydrogen, so of course this reaction will go. I want you to also remember that with these two things being solutions, that we're going to have a net ionic again. And not only that, in a single replacement, it is also redox, always, if the reaction goes, which this one does. So we'll take a look at that here in a little bit. So the question is, what volume of 0.375 molar HCl, so we're looking for the volume there, and here is our concentration, must be used to completely react with 1.25 grams of calcium. So that is a mass, which means we're going to be using molar mass in this stoichiometry in the production of calcium chloride and hydrogen gas. All right, well, let's balance the equation real quick. This one is only going to require a 2 in front of the HCl. Let's write down here what we got. So we are looking for a volume here of HCl. We have its concentration, 0.375 molar. We are given 1.25 grams of calcium. So again, remember that if we got grams in there, we're going to need molar mass to get to moles. So for calcium, that would be 40 grams per mole. So I think we're ready to roll now. So let's do the stoichiometry steps. We're going to start, since we're given our known here as a mass, we're going to start with it, 1.25 grams of calcium, and put it over 1. We're going to convert to moles using its molar mass. 1 mole of calcium is 40 grams, and so the grams cancel. Mole ratio. So our unknown is HCl, so we have 2 moles of HCl over 1 mole of calcium, and those cancel. And now we're trying to find a volume. So the link between moles and volume is molarity. We have it right here. Again, we're going to need to invert it so that we can get the moles canceled and get an answer in volume in liters. So 0.375 moles of HCl on the bottom and 1 liter on the top. 0.375 moles per liter is 0.375 molar. So those cancel, and we're left with a volume. And so to 3 sig figs, 0.167 liters of HCl. And again, if it had asked for that in mLs, we'd have done a quick conversion there, 167 mLs. Not required, but if it was, that's what you do. Just move the decimal or divide by 1,000. Here again, no waste. If we want to completely react this 1.25 grams of calcium, it is going to take exactly 167 mLs of HCl to do that. There won't be any HCl left over. There won't be any calcium left over. Both reactants will be limiting, no excess, no waste. And again, that is a very, very good thing out in industry. So let's go back to net ionic. All right. So again, I'm not going to write all this down. Hopefully we can remember this from doing it not all that long ago. So we're going to have a net ionic because these are both aqueous solutions. So this would be 2 hydrogen ions and 2 chlorides. This would be 1 calcium plus 2 ion and 2 chlorides, Cl minus 1, of course. In a single replacement reaction that goes, remember there is 1 spectator, in this case that would be chloride. And so our net ionic, then maybe I better move this over a little bit. So our net ionic would be Ca solid plus 2H plus 1AQ yields Ca plus 2AQ plus H2 gas. Chloride ion spectators are out. Is it redox? Absolutely. Single replacement reactions always are. As we can see from our net ionic here, both calcium and H2 have an oxidation number of 0. Remember your oxidation number rules. Those are important. They'll be important in our next unit in Unit 11.1. We're going to be coming back to redox again. So only in a much more involved way. But we've got to know those oxidation number rules. Of course, here, hydrogen is a +1 oxidation number. And over here, calcium, of course, is in a +2 oxidation state. So, looks like calcium got oxidized from 0 to +2. And it looks like hydrogen got reduced from +1 to 0. So a little review there on redox. Again, keep that in the back of your mind. It is coming back again. So I think that will take care of the lesson for today. The assignment, solution stoichiometry, would be what you would need to work on for tomorrow. Again, tomorrow, had we been here. And so I'm going to leave you for a minute and sign off. Again, hope this was helpful to you. Like I said, I'm trying to keep things as normal as I can, at least in regards to your lessons, so that you still have the ability to learn and learn and absorb all the material that I know you need to know. So that's the important thing right now. And so hopefully we've begun that and we can keep it going regardless of what happens with school. So anyway, signing off for now. Catch you guys next time. Take care.